Okay, guys, welcome to part two or exercise two of our series on structural analysis with RSAP, Robot Structural Analysis Professional. And today we want to do this exercise as our exercise 221. It's a little bit different from that of exercise one. It introduces an interesting complexity that will cause us to introduce new concepts in our robot so far. So the question is determine the reactions at the supports A and B of the compound beam, and there is a pin at C. Okay, so at C here there is a pin. A pin simply suggests that at that point the beam is not rigidly connected. When a beam is rigidly connected, it allows for internal transfer of shear, axial load as well as bending moment. So it is homogeneous, it is continuous. Okay. When it comes to a pin implies that we are releasing moment to allow for rotation somehow. Okay, so at the level of the pin, there will be no transfer of moment from one part to another. The resistance at that level is zero. So it means if you're drawing internal forces diagram for bending moment, you'll find that the resisting moment at the point of the pin is equal to zero. Okay, so that's important to note. It's important to note. So we release, we allow for rotation at point C. Good. So this is our beam. We have a roller support right here. We have a fixed support here at B, and we have a double triangularly distributed load, right? Or let me just say triangularly distributed load. Okay. Which has its peak at C with 4 kilonewton per meters, and AC is 6 meters and CB is 4.5 meters. So the first thing I would like us to do here is I think we should just go ahead and do the exercise for a change, and then at the end we'll just check to confirm whether the results are the same. Okay, so we'll go back to our robot. We still have our first exercise is what is displayed there. So we want to model a new structure, so we'll go right here to new. Okay, so we'll choose 2D frame again. Okay, because it's another beam, 2D structure, and we wait for the interface to load. So at this point, what's the first thing we want to do? Again, the first thing we want to do is choose our job preference, right? We want to choose the right unit. So you'll notice that in this case, it is the metric system that is being used, right? It is not the imperial. So we want to go to tools and then go to job preferences at the level of units and change to metric, right? Yes, we want to change to that. We can check the details to be sure that it's so. For the dimensions, we want structural dimensions to be in meters, right? Remember, we have 6 meters, 4.5 meters. We want it in meters. And we need the forces. Force, we need it to be kilonewton, yes, moment kilonewton meters, and stresses is not really a cup of tea for now. And again, we are looking for reactions, so the rest doesn't really matter, right? Okay, so at this level, there is one thing that I would like to show before we actually draw the beam. Okay, so it was quite easy to draw the beam in exercise one, and the reason was quite simple because at this level, if I'm coming to draw anything, okay, when I move my mouse, it is somehow already pre-programmed to move certain points. Okay, I don't know if you can see those points visibly, but there are some dotted blue points at the background. Okay, not on the background, on the drawing area. Okay, and my mouse moves from one blue point to those to the other. It can only move on a particular blue point at a time. This is because it is snapped to what we call the grid. Okay, so those blue points, we have blue points, they are organized in a rectangular array. They are organized in a tabular manner. So you have rows of them and you have columns of them. Okay, they are organized in two directions, following the x and following the y axis. You can actually control their span, you can control the way they appear. And I would like by showing that. I would like to start, sorry, by showing that first. Okay. So to do that, you need to come. You need to come right here to view, okay, and under view you have grid. This is where you control all the grid options. So if we click there, you will see that by default our grids here are spaced 5 meters away from each other by default. Okay, it is 5 meters. So what does that mean? It means as I'm moving this point here, as I move here, it is 5 meters. As I move here, and you can see it right up here. Just take the test here. This is -50, right? So the next point it moves is this one. You see that? And here is what? -40. It means the span from here to here is -10, right? Or is 10 rather. Okay. So the middle here should be 5. Okay. So it moves 5 points at a time. Well, we can change that. Okay. So if I go right ahead here and make it 1, for example, following X and apply, you see what changes, right? So this is the X direction, and maybe I zoom so that you see that clearly. You see what has changed, right? So here it is now -25, -24. So the span is 1, 1, 1, 1, 1. While following the Y, we still maintain what? 5, right? So it is 30, 35, and so on and so forth. So for this particular exercise, we will be using grids to draw, okay? So we want to make sure that the spacing that we have between our points is adequate enough for us to be able to draw or represent this, okay? So what we will take is what? Is we will take 0.5, okay? Why not? We could have taken 1.5, right? 1.5 also will do. 1.5 is divisible by 6. 6 is divisible by 1.5, sorry, it gives us 4. And 4.5 is divisible by 1.5 to give us 3, right? So let's try that. We are concerned with the x direction mostly. So 1.5, but for the sake of, let's just put it square grid system and apply. So once we do that, we'll just zoom, okay? We'll just zoom to make sure that, to bring it to a particular scale where we can use it, okay? Good. So that's that. And this grid, you can always switch it off, okay? If you come right here and click here, okay, you can switch the grid off, but it will still continue the game, right? Let me show you something. If I come here to view and I go to grid, right, and I can turn here off or on, and here it will actually disappear in such a way that if I want to draw something, right, I can no longer hang on a particular grid. It may hang on this point, but now you see that I'm free to move to any given point, okay? Now let's try to put the grid back on, okay? Let's put it back on and move now. You see that my movement now is restrained to the points of the grid, which are spaced what? 1.5 meters following the x direction and 1.5 meters following the y direction. That is dx and dy. Okay. I want to show you one more thing. These measurements you see here, the 7.56, 4.5, which helps us to know where we are located and helps us to easily calculate distances, right? We can also shut it off, okay? We can also do away with it if you feel that you don't need it. You can always come and click on view, go to grid and click on that. So it is the ruler element. When we've done this, the grid will still continue functioning normally, okay? It will still continue functioning normally, but we should know what we are doing. Well, personally at this level, I would like to put it back, okay? Just wanted to show you. And you can always click also on adjust automatically, okay? This will set you to uh, something you don't want, most certainly. So please, let's just go back. We'll set you to a distance of 5 at the level of the ruler. Let's just go back and set make sure that our grid is okay. Yeah, 1.5, apply. Yeah, and then zoom normally to where we were. And continue our business. Good. So now we can draw comfortably, right? I hope you've learned something new at this level. So we just take our bar again. We saw that the bar type is simple bar. The section is not relevant at the level of when we're looking for reactions. Okay, so we can go right ahead here and let me start with 0. Let me start at the level of 0 here. I will select the first point, right? So we're supposed to go 1, 2, 3, 4, right? At the level of 6. That's where we are. Okay. Now, I'll need to draw these as two different elements. Okay. And the reason is because of the method that is being implemented in the background of the robot structural analysis software, which is the finite element method. The finite element method, the basic principle is very simple. If you have a complex system, you want to break down your complex system into simpler systems that can be calculated in their local coordinate systems, and then you bring back all the information in the global coordinate system to be able to get the response of the overall system from the different local coordinate systems. So basically that's it. I don't really expect you to understand what I just said, but in resume, if I have a system like this system here was different. It was just one beam. Okay. In this case, I have a discontinuity at the level of the pin. Okay. So I need to separate it into an element this way and an element this other way. Okay. I'll need to draw one, two beams. So I'll need to create a node here. This node will allow me to be able to model a pin at this level. If I just do it as one element, then it might disturb at some point. This discontinuity needs to be represented. Okay, good. So I've drawn from here to here, and then what's left now is to draw from this point, right, to 4.5 now will give us 10.5, right? So we are here at 10.5 to here, right? So we can measure, huh? We can measure and be sure that where is that? Tools, that. If we measure from here to here, this is where we had the point. We see that we have 6 there, and we can measure from here to the end to see that we have 4.5. Okay, that's exactly what we need, right? Good. Uh, let's just undo that and continue. So there is a particular way I just drew now to draw the two elements. I had to come and click here, then click here again, and then click there. But there is a different way you can go about that when the element is continuous in its drawing. Okay, when the previous node is connected to the next element you want to draw, and that way is simply by using this drag option. So let me show you how. Okay, so we'll just undo this. Want the numbers here to start counting from 1 again. Okay, so we'll undo this. I want to make sure that no element or node here exists. Good. So I want the node to start counting from 1, and then I'll start here. So we were at 0. We'll go from is the grid on? I'm not sure the grid is on. Okay, it's on. And the grid is really invisible. Okay, but it's okay. So we'll start 0 and then we go. Is it drawing? Okay, good. And then we go right up to 6, right? So at this level, than for me to come and click here again and then go to 10.5, I can just activate the drag option. Okay, you activate the drag option when the new element you want to draw is related to the previous element. Okay, or rather the new element you want to draw has its first node as the previous node that you just clicked on. Okay, so when you just drag, you don't need to come and click here again. It just pulls the next element from that point, and you can just come here and click right on 10.5. Okay, good. So I hope that helps. That's where we are. At this level, I want to model the supports first. So we'll come right here on supports. Our roller Z is already created, and I hope that if you're starting by any means from this exercise 2, then you should watch exercise 1 to see how we created this roller Z. Okay, here we'll just apply it to the first point, which is this one, and then we want a fixed support at the level of the last point, which is this one. So you see the symbols are different, right? You'll see here a square, you see a triangle here with two rollers. Okay, that's the way it's modeled even in structural analysis, right? These balls show that it can roll in this direction, so displacement in this direction is allowed. This ball shows that it can rotate, okay, so rotation is allowed, but the triangle shows that it cannot move following the y-axis, okay. And here, no rotation, no movement in any direction, as simple as that. So the next thing we want to do from all indices, C has been given the node number here 5. The next thing we want to do is to put a pin support here. And here it is not a pin support. What am I saying? To put a pin here, we don't call it pin support, right? You have to understand that a pin is like an internal fixed, rather, an internal pinned support, right? It allows for rotation but does not enable, uh, what's that? Translation and, in fact, the transfer of displacement is consistent, but the transfer of rotation isn't, okay? Due to the fact that moment, resisting moment there is not, it's not available, or at least in our modeling, it is not, is assumed not to be existent. So how do we model the pin support? Pin support, something is wrong with me today. The pin at this level, how do we do that? To do that, we'll need to go to geometry, okay, and then come here to release. Okay, so what we have to do is we have to break the rigidity at that level and release a particular degree of freedom, which is what? The rotation. Okay, so when I click there, we'll assume that all of this does not exist. Okay, so I'll have to close to delete all of that, and I hope you see the way I'm deleting. Okay, just because I want to show you some things. Okay, so now I want to put a particular, I want to put a pin at this point 5 here. What do? I'll need to create a new release. Okay, on that new release, I'll focus on a bar. Okay, so it tells me beginning and end. Beginning here is the beginning node of the bar, and end here stands for the ending node of the bar. Okay, the last node of the bar. So remember, this will be a bar on its own, this will be another bar on its own, okay, due to the fact that we have separated it, we have drawn it as two different lines. Those are two different bars and two different bins in the finite element method, okay, that Robo uses to calculate its structures. So what do we want to release? This is what they tell you, release directions. Release directions is what we want: rotation around the y-axis, okay? Here we have what? Z, we have X, and if there is any rotation, then it should be around the y-axis, which is the third direction, okay? So we want to release it where? Let's release it at the end, okay? The end means the second node of the bar, okay, and the beginning will mean the first node of the bar. So let's label it as start, released, rotate. I'll just label it like that, and then I'll add that. Okay, so when I add that, I have start, release, rotate, right? So I now need to go and click on my bars to be able to apply them, to be able to apply these releases there. Okay, so to do that, I'll come right here. Now remember, look at the blue arrows, just like we saw in exercise 1. Okay, when the blue arrow is pointing in this direction, what is left towards right, I hope you're seeing the blue arrow, this one, okay? When it's pointing left towards right, it implies that the first node, Robo considers the first node to be the one on the left, okay, and the second node to be the one on the right. So it is always pointing from the first node towards the second node. So when I move in this direction, now it has changed. It is pointing from what? The second node towards the first node, which will be this way in this case, towards the second node, which will be this way in this case, right? Good. We have not labeled this thing correctly, right? we selected end here, but here we said start released node. It's supposed to be end, right? And this name, you can put any name. It doesn't matter. You can put any name. Okay, so let me just do that. Okay, let me delete this other one so that just that one is left. So we have end release node. So it means it is the second node of the bar that I want to release. So what does it mean? It means that when I'm coming to this bar, since it is this 5 here that I want to release, okay, I need to make sure that I'm clicking in such a way that that 5 is the node 2 of this element, and this is the way I'm supposed to click, right? So when I click, did that work? When I click, good. So you will see a release here, right? Good. And then for this other bar, I need to make sure that I'm clicking here, right? To make sure that node 5 is also node 2. Remember, these are the arrows I'm focusing on. And I want to always click on node 2 of the bar because node 2 is what represents the ending node of the bar, right? So I need to click here and you see that it has applied it right here, okay? So this node will have a relationship with this bar and this bar. Okay, so we want it to have to release rotation on both bars. So this will be a pin support for this particular pin. All right, good. So that has solved that. The next thing we want to do is to add the loading. And to add the loading again, we saw that you need to define a particular load type first. And this time around, let's try to change. Let's just put live load just to show that nothing changes, okay? And I'll click on add, okay? And it adds my type here and I can close this. So everything I'm adding now as load will be added under the live load type, okay? So I can come down here and define my load, okay? So what kind of load do you think this triangularly distributed load will be? Well, it will simply be it will simply be um, a trapezoidally distributed load, right? Yeah, where we can indicate two loads, but in this case, P1 will be equal to 0, right? And P2 will be equal to 4. I hope that's clear and that's understood. So P1 will put it 0, 0, so that we can have something like this, okay, 0. And then it goes right up to 4, right? So we'll put here -4. Remember, it is opposite to the Z direction, right? Um, -4. What's left here? Good, the coordinate. So we want it relative, okay? And remember, each of these bars are independent. They are two different bars. It means when I'm clicking on this bar, this is its 0 and this is its 1 when it comes to relative coordinates. And when I'm clicking on this other bar, this is its 0 and this is its 1. So I just want to say this. This tutorial is a series. So if you're watching this as the first video of this tutorial, I recommend that you go back to the channel and then you look at the exercise 1 first before coming back to this so that you're not entirely lost in what I'm saying. Okay, good. So we want it to go from 0 to 1, obviously. Okay, but remember P1 is for node 1, P2 is for node 2, and what do we have to do in this case? So we will need to add this first. What next? Here. This is, we need to make sure that the arrows are pointing in this direction, right? We want this to be node 1 and this to be node 2. And when I click, that's my triangle. For this case, it's different. The triangle is what? Is reversed, right? Is reversed. So this has to be my node 1 because this is where P1 is, and this has to be my node 2 because this is where P2 is. So I need to make sure that the arrow is pointing in this direction from B to C, right? So I will just come here and this is the way it has to be. So when I click there, I have that. As simple as that. So when I close this, we can show our loads and then we can look at it and that's what we have, right? Two different loads on the two beams and we don't see the release here, but you can actually display the release, okay? These displays here are not the only displays available in Robo, okay? If you need to add a particular display, you can always come and click right down here, okay? You see this 4 stuff? Yes, that's where I clicked. You click here and then you have to search. Okay, here we are under favorites, so what is mostly used. And here you see that released is not activated. So if we activate release and apply that, you'll see that now we can see our releases here. I can click on OK. So you have many more options on the display right there that you can play along with and see the changes that it affects on your structure. Um, I think except for the fact that we need to check that the dead load has not added itself to the structure, we are good to go, right? So to check that, we will go to loads and load tables to check all of the loads that are supported by our structure. And what do you see here? You're seeing the self weight, right? We don't want a self weight. We want these two loads. I'll explain them in a moment. We don't want a self weight, okay? So I'll just select that and press Control X to delete it. And here we have this first load that we applied on element 1. Okay, the list here is element 1, element 2. So what are these elements? Let me reduce here. If I go ahead and click here, you'll see this bar here is element 1, okay? And this bar here is element 2. This is what I've activated here. Elements are different from nodes, okay? Elements are the beam themselves. A beam is an element. A column is an element. A bar is an element, okay? So this is element 1 and this is element 2. So we applied a load on element 1, this triangularly distributed load here, and we apply another one on element 2, right? That is what the table right here is showing to us. This one was on element 1, this one was on element 2, okay? And you have these different values that we shall see in a later video, okay? That's that. So what's left for us to do? Well, finish, right? We just need to calculate. Everything is good to go. Yes, they will tell us we have instability of type 1 detected and not 5 in direction RY. Do you want to continue? Yes, I want to continue. And for the instabilities, we'll have time to also look at that in future videos, okay? When you have warnings like that, because it's not an error, this is a warning, okay? So warnings implies that take note of this. Are you sure you want to continue with this? Is something that needs attention. You want to but it is not that the structure is not calculatable. But when you have an error, it's a whole different ball game altogether. Okay, so let's close that. So for the results, let's go again and look at the table results. And I want to take some time to explain this. So when it comes to results for reactions, I hope you saw where I clicked because that's what we're interested in. Reactions, that's what brought this table. Okay, you have 3 columns here. You have Fx, you have Fz, and you have My. Okay, Fx here will indicate to you the reactions that are in the X direction. Fz will be the reactions that are vertical, okay, in the Z orientation according to the local system, that the global reference system that has been given to us here. Z is pointing up, and then Y is our third direction, so this will be moment around the Y axis. Okay, now column 1 here, or rather row 1 here, will be for a particular node, and row 2 here will be for another node. As many rows as they are will be for each node. So the interpretation of this, for example, okay, let me shift that so that we can see. Here is, let me remove the load and try to zoom this. Here is, I'll remove the support too. Here is node 4, as you can see, okay? Here is node 4. So if I go back and look at the results, okay, so node 4, what does it tell me? At node 4, I will have a vertical reaction of 4, okay, and a moment around the y-axis of 0. At node 6, which is which one? This is node 5 in the middle, and this is node 6. At node 6 here, I will have a vertical reaction of 17, okay, and a moment around y of 63. So it will be 63 kilonewton meters. You can see the units right there in the bracket. Okay, so we can now check these results graphically to confirm that it is so. Okay, to do that, let me remove this not. I'll go to results, I'll go to diagrams, and under reactions, we'll select all of the reactions. We want to see all of them with their descriptions, right? And I'll click apply. And when I close this, you can see it clearly, right? So let's try to put back the supports and even the load so that the diagram is complete. Okay, so that's our system, and they ask for the reactions at A and B. So we are deducing that reactions at A and B. We are deducing that the reaction at A is 4, right? Following the y direction. And at B, we have vertical resistance as reaction of 17 and bending moment of 63 kilonewton meters. Okay? So can we check that with the book now to be sure that we are on track? So for that, it is 221. We'll go to answers and zoom this. Okay, so we can see that AY here. Oh, sorry. Answers and zoom this. So 221, what are we saying? 221, we are saying 4 kilonewton at A. Is that correct? 4 kilonewton at A, correct? And then we have 63 as moment at B. Is that correct? That's 63 as moment at B. And then we have 17 as vertical reaction at B also. We have 17 as vertical reaction at B. And that solves our exercise too. Hope you enjoyed it, and waiting for you guys ahead in exercise 3. Bye bye.